Hi everyone, and welcome to the first LimitState webinar of 2023. I'm Tom Pritchard, Principal Engineer here at LimitState, and your host for today's session. I'm joined by Matthew Gilbert, who is the Managing Director of LimitState and also co-developer of the DLO method, more about which you'll learn shortly. Today's webinar is titled The Smart Way to Uncover Hidden Strength in Reinforced Concrete Slabs, and we'll be discussing how you can, with an eye on carbon reduction and adaptive reuse, use yield line analysis to identify reserves of strength in building and bridge structures. And this is going to be illustrated by example using LimitState SLAB, our yield line analysis software. The webinar is going to last around 30 minutes, and there's time at the end for questions, which you can post at any time in the Q&A panel that should be in front of you. If we don't get around to your question during the webinar, then we will always follow up afterwards, answering all the questions by email in the next few days. So without further delay, I'd like to pass you over to Matthew, who's going to introduce you to yield line analysis.
Thanks very much, Tom, and thanks very much, everyone, for joining us for the webinar today. Okay, so just a quick rundown on what we're going to be covering in today's session. I'm basically going to provide a bit of context, and then Tom's going to pick up again and do a demo and then apply the software to various case studies before wrapping up. And there'll be an opportunity for questions at the end. So, context, case for adaptive reuse is now very, very strong. A significant proportion of the whole life carbon associated with a new building is emitted before it's even opened. And that proportion is actually growing as we decarbonize the electricity grid, for example. On the other hand, if we refurbish and upgrade an existing building, then we're typically looking at around 10 times less embodied carbon than demolish and rebuild. So an order of magnitude reduction. And clearly, climate emergency means that we have to do things differently. Business as usual is no longer tenable. In terms of concrete structures, a bit of context. Clearly, concrete buildings have been built widely in the 20th century, continue to be built in the 21st century. Depending on their age, they were designed using a wide range of codes of practice, for example, various UK codes indicated on the current slide, and also a wide variety of different methods. So, for example, Hilberg strip method is sometimes used, is still sometimes used. It's quite conservative, and the same elastic permissible stress design methods are also very, very conservative. Today, we're still using elastic methods via finite element analysis. Unfortunately, they're also prone to provide over-conservative predictions of strength. On the other hand, we can use that to our advantage if we're talking about a structure that's already there, constructed, because the fact that these conservative methods are used means that there's very often hidden reserves of strength. And our task is to identify these so that when we come to repurposing an existing building, we can do so with the minimum amount of strengthening. If we can show that the structure has the strength that's needed in the new use case, then clearly we don't need to spend money strengthening. So, as Tom mentioned, I'm just going to say a little bit about the technology that we're going to be using today. Now, we're basically going to be using something called the yield line analysis method. It's quite widely taught on university courses, but certainly not on all. For those of you who don't know about it, it's an upper bound plastic analysis method that dates back to the 1920s. The nice thing about it is that you can get a direct estimate of the collapse load. So you basically you postulate a failure mechanism, and then it's very, very simple to work out the associated collapse load. And it comes up with much more realistic assessments of the slab capacity than some of those other methods that I was referring to in the last slide. The only downside is that it's non-conservative if you choose the incorrect mechanism. We'll come to that shortly. In terms of scenarios where yield line analysis has been applied. A couple here. One, building slab case. Yield line method was used in parallel with a whole series of different methods, elastic methods, in the design of a reinforced concrete frame structure at Cardington about 20 or so years ago. And what they found was that the yield line method led to the least reinforcement being required, and also very simple reinforcement in terms of configuration. So that's in the design context. Again, if we switch this around and look at the assessment context, this is demonstrating that there's likely to be significant additional strength in a building that was designed elastically. Next example is a bridge example. Some very nice work was done in the 1990s and 2000s by Middleton and co-workers at the University of Cambridge. They applied the yield line method to a whole series of bridges. You can see the bar chart shown where the elastic assessment indicates the elastic predicted capacity in red. In green, we've got the plastic assessment with clearly a much larger bar. And in the vast majority of these 21 bridges, the plastic assessment indicated that the bridge actually had the capability to carry 40-ton vehicles, whereas none of those bridges was predicted to have that capacity when an elastic assessment was done. Right-hand side shows failure mechanism, a sort of library of failure mechanisms that was considered in the software that Middleton and co-workers used for this purpose. You can see there's a whole series of different mechanisms. The only problem with the method is that if you have a different geometry of bridge or a strange configuration of reinforcement, then potentially a different mechanism could have been critical. So there could be a mechanism number 28, which was actually critical in this particular case in question, which, as we have heard already, would lead to a non-conservative prediction of strength. So that was the downside of this this approach that Middleton and co-workers applied. So the way we've addressed that is by systematically automating the yield line method via a technique that we've coined discontinuity layout optimization. And with discontinuity layout optimization, or DLO for short, there's no need to work through a series of predefined mechanisms. It will automatically find a critical mechanism, irrespective of the geometry, reinforced configuration, and so forth. So it's a systematic automated method. It turns out that we can solve the problem as a simple, albeit large-scale, linear optimization problem. And if you're interested, there's various papers published in the 2010s that you can see on screen. In terms of how it works, basically, imagine you've got, for example, a square slab with fixed supports. The way we tackle that with DLO is we populate the slab with nodes. We then interconnect those nodes with potential discontinuities, in this case yield lines, and then we use optimization to find the critical yield line pattern. And if we use more nodes, we tend to get a more accurate representation of the collapse load. And we've showed in those papers that very, very quickly you get within around 1% or so of the exact solution. So you get very, very good predictions very, very easily. And that overcomes one of the major weaknesses of the traditional yield line method, which is that it's prone to come up with non-conservative solutions. That's the case by hand. When you automate it in this way, there is really no danger of that. Okay, so I'm now going to hand back over to Tom, who's going to give you a demonstration of how the method can be applied in practice.
Thanks, Matthew. So I'm just going to open up LimitState Slab here. You can see we're starting just with a blank canvas. I'm just going to give you a quick flavor of how the software works and how easy it is to set up and solve a problem. So first thing I do, we need to define ourselves a geometry. So I'm just going to draw a reasonably random shape slab on the screen. You can see there, if I turn off the grid now, we can see we have this shaped slab. The next thing we need to do is apply some boundary conditions to it. Just for the sake of speed and simplicity here, what I'm going to do is select the entire problem, subselect the external boundaries in the property editor on the right-hand side here, and you can see the bottom field allows us to change the support type. For external boundaries, we have a choice of various ones. In this case, we're just going to go for simple supports, but we could equally choose fixed or symmetry or partially fixed supports, depending on the problem at hand. So we have a geometry, we have our support conditions. The two things that we need to apply to it now are some sort of material properties and also some loading. So the first thing I'm going to do is just define what we call a structural definition. It's a flexural one. We're going to call it new structural definition because that's what's been suggested. And then for the sake of this, we're just going to have in the first and second directions an MP of 1. So what we can do is actually apply MP of 1 in hogging and sagging in both of the Cartesian directions. The thickness and the unit weight of the material come into account once we start taking into consideration the self-weight of the structure. So if I click OK, I can now just drag my structural definition onto the problem. You can see it's turned a darker blue color to show that that's been applied. So the last thing I need to do now is apply some weight to that in order to drive collapse. What we're going to do is add a pressure load over the entire structure. So if I click this icon at the top here and select all, we can see that our one zone has been selected. And if I click OK, we're just going to apply unit pressure to it, and the action type is unfavorable, so it's driving the collapse downwards, and we've set adequacy to be true, and that I'll explain a little more in a second. So if I click OK to that, we can see now around the edge of the zone we have this red line, which is indicating that there's a pressure load applied to it. So we have all the constituent parts of our problem there for us. We have a geometry, we have boundary conditions, we have material properties, and we have loading. So the last thing I just need to do is click on solve, and we can see, as Matthew demonstrated a little earlier in the PowerPoint, the software builds towards the critical collapse mechanism and very quickly in this case has identified what that collapse mechanism is, and also given us an adequacy factor, in this case of 2.34. And what that means is that the load that we have applied to the problem can be multiplied by 2.34 in order to reach that collapse state. And if we look at the problem itself, we can see we have red and blue lines for the yield line pattern, and the thicker those lines are, the more rotation we're having in the problem. And the easiest way to see this is if I animate it, we can now see that actually the problem has failed in that manner. So we have our adequacy factor of 2.34, so we know we can multiply our pressure load up by that amount. We may also wish to look at that in a report. So if we click analysis and report, we have the number of options that we can choose from to actually include in the report. I'll just select them all, and we can see here we have our critical mechanism, we have our adequacy factor, and we have some information about the problem. So that's a very, very quick outline of just how the software works and how easy it is to set up and solve a problem. What we're going to do now is jump back into the PowerPoint. Actually, from the demonstration, just a quick summary, actually. So we're saying that the yield line method is automated, so there's no need to worry, like Matthew said, that the critical collapse pattern has been missed. The software will find that automatically for us. It determines the true capacity of the slab, so ascertains whether an existing structure is strong enough for any proposed modifications, and we'll touch on that shortly. You can quickly and easily check for the influence of those modifications. One thing that people may look towards is using elastic FEA as an alternative. However, with that sort of approach, you need to make adjustments for column perimeters and such like, and there's no redistribution of moments. So there's a danger of under-predicting the capacity. And as we all know, many slabs have been designed using many different methods, and we want to ensure that we're able to make best use of all those structures. So we're going to take a look now at a case study, and this first case study is for adaptive reuse of a building. So what we have, and what we'll see in a second in SLAB, is a multi-story building with columns, which we can see here, and a balcony to the left-hand side. And on the right-hand side of our problem, we have a line of symmetry. So you can imagine that this is actually twice as wide. The size of this slab is actually around 6 by 8 meters, and the client knows the existing reinforcement scheme, so we can use that in order to then calculate MP values to enter into LimitState slab. The internal columns, as we can see here, the tops will be provided with a different structural definition, and on the left-hand side here, where we can see this pink zone, that's the cantilevered balcony. So the two questions that the client wanted to ask about this is, firstly, can the slab carry two 25 kilonewton props? So in this case, in this left-hand section of the slab here. And then the second question is that following the refurbishment works where these two props are going to be present, they'd also like that left part of the slab to carry, in the long term, an additional 2 kilopascals of loading as a pressure load, and would like to understand what effect that has on the structure. So if we jump back into LimitState slab, I will open the first of these files. So you can see here, this is the same problem that we just saw on screen in the presentation. We have the different structural definitions in the left-hand side here. So we have the slab, which corresponds to the main body of the problem with our MP values here. You can see it's got sagging reinforcement, but 0 for hogging. For the column tops, though, we have much higher hogging capacity. And then for the balcony, similarly, we have a combination of sagging and hogging. If I toggle on the display of the loads in the problem, we can see, as before, we had this pressure loading, but we also have these two 25 kilonewton point loads that are applied. And if I open the load case manager, we can see here where those have been specified. So we have in the load case manager self-weight loading, we have the pressure loading, both live and dead load for the balcony and the slab, and we have these two prop point loads. And those are all defined in this loads database here, as you can see. And then that means that they're available for selection within the load case manager. We also have some EC0 partial safety factors. If I click that button there, you can see we have permanent variable and accidental partial safety factors. If we wanted to further vary those by favorable, unfavorable, and neutral actions, we can click that and actually specify it on a finer grain level. But for the sake of this, that blanket permanent variable and accidental is fine. So now if we solve this problem, we've got a fine nodal density we can see on the right hand side here, which means that we have about 1,000 nodes within the problem, and it'll take a little while to solve, but we can see relatively quickly that we go from this sort of first guess in the optimization through to a final result, which will take just a few seconds. So here we are, we've got this final solution here now. It's quickly identified the critical collapse mechanism. And as we can see, as I mentioned previously, the thicker lines here represent the areas of larger bending in the problem, or more larger rotation, should I say. So we can see here we've got what looks like a fold at the left-hand side, and then these two arced areas at the top and the bottom of the slab. If I play the animation, that confirms what we've just said. So we can see at the left-hand side of the slab here, we have this bending, and then at the top and the bottom, we have those two arched sections, which are also collapsing. And the question that we were asking in this particular case was, can the slab resist that extra loading of those two props, which we can see here as the pink dots? And we can see our adequacy factor is marginally above 1 for this, which suggests that yes, it would be able to take that extra loading, and that's the first of the questions that has been answered. If we go now to the second question, which is what happens for an extra 2 kilopascals of load on this left-hand side of the slab here. What I can quickly do is, first thing we want to do is just demarcate that left-hand side for where we want to be applying this loading. And then in the load case manager, come down, we have our list of pressure loads. If I just select additional live load, make it unfavorable, the adequacy is true because we want to be increasing that to drive collapse. And if I click change, I can then select this left-hand zone here as being the one that is subject to that additional loading. If I click OK and solve, as before, what we'll see is that the software works through relatively quickly to determine what the critical collapse state is. And we can see here, we've lost that fold on the left-hand side now, and more of the yield line pattern is concentrated on the right-hand side. And we have, again, this folding of the top and the bottom of the slab, but also collapse towards the right-hand side where that symmetry line is. If I just jump back to the presentation, our two questions were, can the slab carry the two 25 kilonewton props? And the answer to that is yes, the adequacy factor was above 1 for the factor problem, so that's okay. And then the second question was, what effect does adding an extra 2 kilopascals live load over the left-hand zone have? And we saw there that the adequacy factor was also above 1, so 1.05, so also okay. But the yield line pattern here is suggesting that actually there's not much of the failure pattern in this left-hand side. If we'd applied that 2 kilopascals load on the right-hand side, it may have been a different case. So just to jump into the second of our case studies, which is one to do with an abnormal load on the bridge. Our problem in this particular case is one where we have a rectangular slab section of a bridge deck, and this bridge is on the proposed transportation route for a wind turbine, which the vehicle carrying it will have 10 axles and a total weight of 96 tons. So sort of double what you would normally expect to be taking over such a structure. And the question we want to answer here is the bridge slab strong enough to carry this abnormal vehicle? And we can see here on the right hand side, we have the details of that vehicle. So either 7.5 or 10.1 ton axle loads. We have the spacing, and this isn't actually the vehicle in question, but it's one that's very similar to it, just to give you some context. So again, what we'll do is we will jump into LimitState slab. We can see here, actually, I've rotated the slab by 90 degrees just to fit onto the screen. And if I show the loading, what we have is our load vehicle here is represented by a series of point loads. And we also have this green line, which is a line load, which is a safety barrier, which in the great scheme of things, if we've got a 96 ton vehicle, probably won't make that much difference, but has been included in there just to make sure that everything is right. If we click on the load case manager, we can see in this case what we've actually done is we've set up a number of load cases to represent the vehicle moving across that slab, so we can see where the critical loading position is and find out what the adequacy factor is that is associated with that. And in order to do that, I won't do it here, but all we would do is select whichever loads we want to copy, and then if we go to action and copy, we can then copy those to new load cases with an X and or a Y offset. So that's effectively what we've done here for these 6 different load cases. And if I scroll through them here, maybe zoom out a little, we can see the vehicle moving from left to right across that bridge. So if I solve, as before, what happens is that the software finds the critical collapse state, but in this case, it's doing it for each of the 6 different load cases. You can see that changing on screen as it goes through the different tabs which are associated with those load cases. And then once it gets to the end, it's found that actually load case 2 is the critical out of the 6 cases that we've looked at. And the adequacy factor that's associated with that is 1.25. So we have our partial safety factors applied. So 1.25 means that we are confident that the structure will be safe under that loading. If I just turn the view of the loading back on again, we can scroll through and just see actually the different failing mechanisms and how they correspond to where the wheel loading is at any one particular point. So if I go back to the case study in PowerPoint, we can see the question was, is the bridge strong enough to carry this abnormal vehicle? And the answer to that is yes, because our adequacy factor for the factored problem was above 1. What we would say in this case, though, is that this was a relatively small number of load cases that were considered, and we should have more load cases and potentially put more nodes into the problem to be certain. But for the purposes of the demonstration, yes, it was safe. So if we come to summarize now, for LimitState slab for adaptive reuse, we have demonstrated that you can quickly assess the real flexural capacity of reinforced concrete slabs in existing structures, and that is likely to reduce the amount of intervention that is required either when you're repurposing a building or if you're looking to carry different load cases across existing infrastructure. The underlying automated yield line technology is proven and robust. So Matthew linked to a number of different papers, and the software hopefully has been shown to be easy to use. So you should be able to pick it up and use it straight away. If you want more information about the software, then you can get that from our website, which is LimitState.com/slab. So we've got maybe a minute or two just to answer any questions. So if you have any, please feel free to add them into the software. So the first question is geometry optimization considered in the software to get a more accurate solution? So Matthew, I think, wants to answer that one for us.
Yeah, so good question. The answer is no. Geometry optimization is really good at sort of rationalizing a yield line pattern, making it look prettier. It doesn't make a very big difference in terms of the answer, certainly with the nodal resolutions that we're talking about. So it's not going to make a very big difference. It's going to reduce it by 0.1% or something of that sort.
So we have another question is, which codes allow for using this method? How does the EC2 relate to this?
Yeah, so certainly EC2 allows use of the yield line method. So there's no problem applying EC2. So here, clearly we're moving from retrofit to new design, which is obviously a bit of a different webinar, but yeah, absolutely, yield line method can be used for the design of the new structures as well as for the analysis of existing ones.
And I've just got time for one more question. And could the software be used to analyze a waffle slab? And if so, how would it best be modeled? Yes, is the answer. It could be used. The best way to do it is, I won't go into the software right now, but you can quite easily set up the geometry into squares and assign different structural definitions to the different areas. So you're not constrained to one particular geometry. You can put in whatever you like, and as long as you have the MP values for the different areas, then you can assign those with different thicknesses as you see fit. So that's brought us to the end of the webinar. I'll just click through the slides. So I'd like to thank Matthew and also to everybody who's attended the webinar today. A recording of it will be posted to our YouTube channel in the next few days. Please be sure to like and subscribe for that. And you can find out more about LimitState Slab, as we said, on our website at limitState.com/slab. You should also be able to download a trial of the software from our website also. And if you do have any questions about the things you've seen today or any of our other products, then do feel free to get in touch with us on info@limitState.com, and we'll be more than happy to answer all of your questions for you. So until next time, just like to say thanks again for joining us, and we hope to see you again soon. Bye.